Okay, let's begin. Good morning, everyone. Hello, and welcome to the fourth day of the GeoNetcast America's Eastern Caribbean Training Workshop. Before I begin, I just would like to remember that all the resources that we will see today, like presentations and um, links and assignments, you may access these resources and download them in our Moodle, okay? And just send the link to our Moodle page in the chat box. Also, if you click in announcements at the top of the page, you may access all the links shared in each day. So for example, here, links day 1, you have the links shared during the first day, okay? Here, links day 2, you have the links for the second day. And here, the links for this Monday. Okay, and you also may access all the presentations from the previous days, the training agenda, a GitHub repository here with all the example scripts that we are seeing during the training. They are all available for you to download. Okay. The Zoom link, you have all the complementary activities in the beginning of the page with an overview of the recent satellite products, the data access mechanisms that are available, and some of the visualization tools. You also have a procedure on how to install NASA Panoply, as we have seen on the first day, and we are going to explore a little bit more this Friday and next Monday. And you also have a couple of tutorials if you are interested in processing files that you receive in your GeoNetcast America's ground stations with Python, but locally in your own computers. During the training, we are seeing how to run them directly in the cloud. If you want to run them in your machines, you have a couple of procedures here. Okay. All right. This is our day number 4, and we will start the second half of the training. During the third day, we started with the homework reflection and learned that how to create the night fog difference and the split cloud phase difference. And then we learned details of the Nova S300D receiver, how it works, how to install the tools to connect to it and monitor the GeoNetcast America's reception parameters. Okay. And we finished the day starting the NWP data processing examples, right? And in these examples, we process data grid files from GFS, but you may use the same concept and almost the same script to process data from other models like ECMWF, WRF, and others, okay? Today, we will start with the Python homework reflection and see how to create the split water vapor and split ozone channel differences directly in the cloud, okay, in Google Colab. You should have your notebooks ready now for this session. And if you haven't already, please create a copy of the homework notebook available on Moodle here at the end of the second day, right? Please create a copy of it and run the first cell of code. This one, installing the necessary libraries and download the ancillary files, okay? And after that, we will learn more details about the FAZZT professional client and the software used to receive and manage the files that the data providers upload to the GNC-A system. And we will also check the specifications and more details of your workstations. And in the hands-on activities, we will see a maintenance checklist and a maintenance flowchart and learn which parameters we need to check during a maintenance and what they mean, okay? And we will finish with the second part of the NWP data processing hands-on with Python. Okay, and also just to remember, today before the break, we are going to take a group photo, right? So please turn on your cameras before the break so we can take a screenshot. And now let's open our GoZar homework Colab notebook and create the split water vapor and the split ozone channel differences. Just a moment. And I will open mine. And this is it. This is our homework notebook, okay, that we have been using since the second day. And apart from the first three examples, example number one, split window difference. Example number two, the air mass, RGB. And example number three, the day cloud phase, RGB. We have already processed two channel differences, right? The first one for the assignment number one, the night fog difference. We have created a basic plot, right? And we have learned how we can show only some parts of the data to, for example, to display only the positive values, just like it is displayed in the geocolor composite at the series slider page, right? And in our second assignment, we have learned how to create the split cloud phase, subtracting channel 11 from channel 14. Okay. And we have created the first plot, and then we have changed the color maps. And we have seen that with it, we can enhance some features. In this example, we have an eruption here. However, as we have seen in the quick guide, it's not appropriate to use channel differences alone to enhance eruptions. And on the next day, we will see very nice examples with the ash, dust, and SO2 RGBs. But today, we will see a couple of channel differences more, right? The split water vapor, the 6.2 micron band minus the 7.3 micron band, and the split ozone, the 9.6 micron band minus the 10.3 micron band, right? And in your notebooks, you have this, an empty code cell, right? And you may write your script here, okay? Now let's see how we can create the split water vapor difference, right? So the difference, that's the difference between the 6.2 micron band, that is channel 8, or the upper level water vapor, and the 7.3 micron band, that is band 10, the lower mid-level water vapor band. First, let's open the quick guide, and I will send the quick guide link in the chat box. And as we see here in the description, the difference between the two bands gives an approximation of the concentration and distribution of water vapor, okay? Also, the pixel values that are near zero over thick high clouds. Values are very large and negative, where small amounts of high-level moisture are present, and values are negative in a very dry atmosphere. Okay? Now let's see how we can create this difference. The procedure is basically the same, followed to create the brightness temperature differences, or BTDs, right, for the night fog and split cloud phase. First, we need to copy our example number 1, the split window difference, right? You may copy the content of the cell as this, right? Or you may click at these 3 points here and copy cell, okay? I'm going to copy the content and paste it in the assignment number 3 here, split water vapor, right? And if I run the cell code as it is, just as I pasted, you see the split water vapor difference. Okay, so as you've seen here, the files have been downloaded, and right now it is generating the plot. Okay, let's wait some seconds more. And here you have the split window difference from the second day. But we want to create the split water vapor now. Okay, so we need to change some parameters. First of all, I'm going to change the title, right? Here, I'm going to add split water vapor difference in the comment section, right? Then we have our libraries, and the libraries are the same. So you can use the same libraries as we have used it in the first example. The input and output directories that we are creating with the OS library, they are also the same, right? And we are using the make clears command to create these libraries in our virtual machine in Google Colab, called samples to store the netcdfs we are downloading from the cloud, and output to store the PNGs, okay? And for the date, I will add 2019, 11, 24, 17 UTC, right? And let me check the bands that I am downloading. For the split water vapor, as you see here, we were downloading bands 13 and 15 using the download CMI function. But for this difference, we will download band number 8 and 10. Band number 8 and band number 10 for this date, okay? And by the way, I'm just adding this date here because it's the same date of my air mass composite from the second example, because I want to compare my channel difference with the air mass composite, right? Because my channel difference is part of the air mass composite, okay? All right, so here we download the files, okay, for bands 8 and 10. Band number 8, I'm calling it data 1, and band number 10, I'm calling it data 2. Okay, so I'm reading the brightness temperatures that are called CMI, or cloud and moisture imagery, as it is called by NOAA. And I'm storing this brightness temperatures in the data 1 variable and the data 2 variable. But I can call these variables the way I want, right? Here I'm creating the channel difference. Data, or my split water vapor, is equal to data 1, or band 8, minus data 2, band 10, right? To make things easier, I can call, for example, data 1, I can call it data channel 8, for example. And data 2, I can call it data channel TH10, and change here. Data 8 minus data 10. And I can call data as data split water vapor. SWV. However, I need to, in my imshow command, I need to insert the right variable, data SWV. Okay? And I'm also going to change the color map as suggested here to IP spectral, IP underscore spectral, and change the temperature ranges to -30 to 5, -30 to 5, and call it split water vapor, and call my legend split water vapor. And I have created these variables here so it's easier for you to change them. But remember that I'm using this color map variable inside my imshow command from matplotlib pyplot module. And I'm using this V minimum and V maximum here, V minimum and V maximum. And I'm using the title here. And I'm using the legend in the color bar here. So I could have added these commands directly in each line. But to make things easier for the homework, I have created these variables, okay? And let me run the code cell. And I can run it clicking here at run at the play button, or in my keyboard with Control plus Enter, which I find much easier, okay? So it is downloading a file for band 8 and a file for band 10. And with the green arrow here, you may see the current step, okay? And after some seconds, you will see the split water vapor. This is the split water vapor channel difference, right? And as we may see in the quick guide, values near zero here in orange, in our case, right? Because we have configured our color map this way. Values near zero are over thick high clouds here, here, or here. Very large negative values, in this case between dark blue and purple, is where small amounts of high level moisture are present, like here, okay? Also, where values are negative, in our case, in tones of green, we have very dry atmosphere. If we look at the RMAS RGB quick guide, let me open it here. RMAS. This is it. I'm going to send it on the chat box. We will see that the split water vapor difference is the red component of that RGB here, 6.2 minus 7.3. And it physically relates to vertical water vapor difference. And large contributions means dry upper levels. And that is why if we compare two images for the same time, we will see that where we have negative values here as green in the split water vapor difference, in the RMAS composite, we have these regions in orange, where we have a greater contribution of red, okay? And if we look at another RGB, which is called the differential water vapor, We also have vertical water vapor difference contributing as red, right? And as we can see in this quick guide, RGB is used to identify upper level moisture boundaries, ridge patterns, and potential vorticity anomalies. So these RGB also uses the split water vapor in the red component. And as you see here, an orange color means dry mid upper level. And a dark orange, as you see here, means very dry upper level. Okay. And we can also see this RGB in the DSAT webpage or in Series Slider. If you open DSAT and select differential water vapor, this is what you will see, is RGB, okay? And here you may see, as the quick guide says, tones in gold, dry upper level, moist mid-level or mid-level cloud, tones in gold, right? And pixels in orange, dry mid-upper level, here. And pixels in bright orange, very dry mid-upper level, okay? So this is the differential water vapor, RGB. And the split water vapor difference, as we have created with Python, is used as the red component of the RMS RGB and the differential water vapor RGB. Okay, so that's the split water vapor difference and our assignment number 3. If you have any questions and if you do not understand any or some of these commands, let me know. Right? Send me a message in the chat box, and I can return and explain any one of these commands. It's very important, as we have mentioned since the first day, that our examples are getting more and more complex, and that it's important that you understand all of them since the beginning. Okay, and if you do not understand, or if you have any problems running these scripts, just let me know. And I'm very happy that I'm receiving some emails from participants that are trying to run these scripts, that are trying to run them locally. And most of them are being able to do that, which is great. Now let's create our assignment number 4 and create the split ozone difference. And the split ozone difference, we need to subtract the 10.3 micron band or band 13 from the 9.6 micron band or band 12. Okay. Again, the first step, let's copy our first example, right? From example number 1. I will copy the content so I don't need to start from 0. And that's the nice thing when we start to get accustomed with Python and these scripts, because in the end, as we are going to see on the last 2 days, in the end, we are just copying and paste fragments of code and creating new things. And as in our presentation from the first day, there's a gradual learning curve, but with time, we will learn more and more tricks, and you will be able to create more plots. Okay, let me paste it here. And as we did in the third assignment, I will change the title to split ozone. Okay. And the first step, again, is to change some of the parameters, right? I will use the same date from the RMS 2019, 11, 24, 17 UTC. And the nice part of this function here, called download CMI, as we have seen on the second day, is that you may insert any date you want. Of course, since the launch of Go 16, and as long as it is available in the Amazon Web Services. Okay. For this date, it is available. Okay. And I will change the bands to band number 12 and band number 13. band number 12, and band number 13, right? And I will call data 1 as data channel 12, and data 2 as data channel 13. Data channel 12 minus data channel 13. And I'm going to call my variable as data underscore split ozone. But I need to change it here also in the imshow command. Okay. And as we can see in the quick guide here, the split ozone difference can reveal the influence of ozone absorption compared to the clean window, that is the 10.3 micron band. Okay. And high clouds have positive or near zero values, right? And clear skies over warm water show large negative values. And clear skies over land show negative values. Let us create this difference. I will use the 90 spectral again. 90 spectral. And my range is between minus 45 and 5. Minus 45 and 5. And I'll call it goal 16 split ozone difference. Split ozone difference. Let me run. I will change to image split ozone.png and run the cell. The files are being downloaded. The first file and the second file. After some seconds, we have our split ozone difference, right? So high clouds have positive or near zero values. And according to the color bar we have just created, values, positive values, or near zero values, they have tones of red or gray. As you see here, tones of red or gray, right? And please note that this is different from the color scale used in the quick guide, right? Because I'm using a color scale that I want. So you need to consider that during the interpretation as well. Low clouds or clear skies over land show negative values. Green tones, in our case, here. Okay. And clear skies over warm land or warm water shows large negative values, as here, as blue or purple. Okay. And if you look at the air mass quick guide here, the split ozone is the green component of the air mass RGB, as we see in the quick guide here, right? And it physically relates to tropopause height based on ozone and small pixel inputs or small contribution means low trop and high ozone, and large contributions mean high trop and low ozone. Okay. And as we see here, for example, right, greenish tones also mean low level clouds, as we see in the R mass composite of the Colab notebooks here, for example, right? So this is it. This is our split ozone composite. And that's our homework reflection for today. And here we finish reviewing split uh, the four channel differences: night fog, split cloud phase, split water vapor, and split ozone. There are more, but for these examples, for you to practice, these are the four examples that we have studied. And the objectives of these BTDs, or brightness temperature differences, is that you understand how to create channel differences, how they are used in the creation of RGBs. And talking about RGBs, this Friday, we should start creating other RGBs following the recipes, right? And on the next day, we will see the dust, the ash, and the SO2 RGBs. Assignments number 5 and 6. So please try to create these RGBs before the next day. And if you have any questions, just let me know, okay? If you have any difficulties. And just some hints before you try. Um, uh, avoid starting from 0. You may just copy the code from the ARMAS RGB, okay? Copy it and paste it here, assignment number 5. You may paste it here as your starting point. And based on previous training, when participants try to create these RGBs for the first time, they usually forget to delete this instruction here. Convert the blue channel. That's necessary only for the RMS RGB. That's not necessary for the other RGBs we are going to see. And another thing they usually forget is to change the gammas. As you see here, for example, in the dust RGB, the gamma for the green component is 2.5. And in the air mass, it's 1. So here in this variable, you need to change the gamma from 1 to 2.5, okay? So that's it for the homework reflection today. And now let's return to our first presentation. And today we are going to present the FAZZT professional client in detail. And it's the software that manages the GeoNetcast America's incoming data. And it is the only component of the station that has a single supplier in the market. All the others, the receiver, LNB, workstations, you have many options. But for this one, there's a single option, right? We will see the details of the GNC-A uplink station. We will introduce the FAZZT client, review how to install the software, how to configure the software according to our needs, and how to monitor incoming files. And most importantly, check the quality of our reception, which gives us a good idea if we should improve the alignment of the antenna and other important information, okay? And this is the GNC-A simplified component diagram. And here, we see that the GNC-A station, uplink station located at Georgia in the US, the content is uploaded by the data providers, right? And it is encapsulated by the GNCast FAZZT server and uplinked to the broadcast satellite, Intelsat 21 in our case, right, at 58 degrees west. Then the linked data is rebroadcast by the satellite and received at ground stations. Ground stations antenna and the LNB, as we have seen in the second day, the antenna captured the broadcast and pass it to the receiver. And the receiver, as we have seen this Monday, it converts the broadcast into a digital string that can be understood by a computer. And finally, the FAZZT client listens to this data stream and encapsulates the data and then changes or then manages how and where the data is stored in the computer according to the user configuration. Okay. And when we talk about encapsulation and unencapsulation, right, or de-encapsulation, we just mean that in the server, some information is added before the data, which is known as header. And also information is added after the data, which is known as trailer. So that's the encapsulation process in the server, okay? Then in the user side here, uh, the client, the FAZZT client, performs the unencapsulation, and it basically removes this header and trailer information, and it is able to process the file. So in summary, the FAZZT server is used in the uplink. So FAZZT client must be used in all ground stations, okay? And as we have mentioned in the first day, FAZZT is the only component of a GeoNetcast Americas station that has a single supplier. It is used in all stations. And here we have some screenshots or photos of some stations from Argentina, Brazil, Belize, Peru, Costa Rica, and Honduras. And they all use the FAZZT client, as you see here, right? And over time, manufacturer releases a new version of this software. And the most recent version is version number 10, right? Which is a version installed in the stations of the project. However, as you see here, there are users with different versions, like version 8, version 8.2, version 9.1, and 9.2, and so on. Any version of this client works with GeoNetcast Americas. The only difference, apart from the little enhancements of the interface, the difference is the operating systems that are supported by a particular version. Older versions of the software were only supported Windows and Linux Red Hat version number 6, like CentOS 6, for example. And the most recent versions, like version 10 and 9, they support the most recent versions of Windows, CentOS 7, and Ubuntu. Okay? And a very important detail is that this is a one-time license or a perpetual license. So there's no recurring costs once you purchase the license. So there are GeoNetcast Americas users that run their stations using very old licenses, like this one here, version 8, without any problems. Of course, considering the operating system's limitations, okay? Um, and the client, the FAZZT client, basically manages how and where the data is stored in your workstations. And NOAA gives an IP, a password for each data provider of the system. And these providers upload data through FTP using these credentials, right? And in the user side, each channel is seen as directories, as we have explored in the first day. And in your ground stations, you may find the files at css/data/satellite/FAZZT. But as we have seen in the first day, we may explore the GeoNetcast Americas ingestion directory in this link here, as I have sent in the chat, kindly provided by SIMS. And here you have the ingestion directory. So every one of these channels, of these directories, is a broadcast channel, as configured by NOAA, right? So you have a folder for SIMS, a folder for Sierra, and for the other data providers, as NPIG, for example, where I work. And you have, in some cases, same data provider has many directories, like NOAA, which is the main data provider of the system. They have a folder called Goals Are CMI Imagery with all the 16 bands. Those are level 2 products with all the level 2 products. Okay. And all right. And so this is it, right? And an additional comment is that the FAZZT client is also used in another system called the Himawari Cast, provided by GMA, or the Japan Meteorological Agency. And this is one of the systems GMA uses to disseminate information from the Himawari satellite, as you see here, right? And here you have the coverage of the system. Here you have the types of image available in the broadcast, and here an example of antenna. And as you see here, it's very, very similar to what GeoNetcast Americas is, right? And as you see here, FAZZT client is used to unencapsulate the data for storage in any directory on the computer. So this is a very similar system, but it's for users in the Asia Pacific region, right? And users of the Himawari satellites, Himawari 9 and 10, I think, right? Okay, so the FAZZT solution, both server and the client, they are developed by a company called CanCast, and it is from Connecticut. And this company is specialized in end-to-end control of sending and streaming content for multiple sites and secure content delivery, right? Like, as you see here, digital cinema, digital signage, and mobile video delivery. So the FAZZT client is one of the products provided by CanCast. And it allows users to monitor incoming transmissions, tune across channels, run scripts, view statistics, and configure and receive channels, as we are going to see, okay? And when you purchase a license, podcast, you send you a physical CD, right? Or it may provide you a FTP link with the CD content that you may download. And most users prefer getting the content using the FTP link, so they do not have to pay possible importation taxes to get the physical CD or the physical media, okay? And this is the content of the CD, and the most important folders are these ones. Third-party, with third-party software, like the database used by FAZZT. Doc folder with the user guides and user manuals, and the FAZZT folder with the installers. And inside the FAZZT folder, you have a Linux folder with installers for Linux and a Windows folder with installers for Windows. Inside these folders, you have here, for example, as we see here for Linux, you have latest versions that support Red Hat, right, or Ubuntu. And for Windows, you have an executable file that supports Windows 7, 8, or 10 and 11. Okay, so these are the most important directories when you receive the FAZZT CD, right? And these have been the steps followed by EEC, which is the vendor that provided your turnkey solutions. So I'm presenting these steps here because for you to understand what they have done in your ground stations. And in the future, if you need to install this software in other machines, you are perfectly able to do that. Or suppose that some of you want to assemble a station from zero, right? Which is much, much cheaper. You will also be able to do that, okay? And here we have some screenshots of FAZZT running on Ubuntu, running on CentOS 7.9, as in the stations of the project, and Windows. Most users runs the FAZZT client on CentOS, as in the stations of the Caribbean project. But there are also many users running it in Windows or Ubuntu, right? And as we are going to see, that are many tutorials available on the blog for the installation in each one of these operating systems, okay? And also there's also a README file in the CD, right, with the instructions of how you may install the software. But in the blog, we have more detailed information and the steps are more easy to follow, okay? Also, FAZZT needs a database management system that it uses to manage the files from GeoNetcast. So before installing FAZZT, we need to install and configure the database. On Windows machines, the Microsoft SQL server is indicated. And for Linux-based systems, PostgreSQL is the database used as it happens in the stations of the project. Installing and configuring a database, it's not trivial. It's not easy. But fortunately, the process is automated using scripts, as we are going to see. When talking about versions, the stations of the project have FAZZT version 10.0.0.1 installed, okay? And CentOS 7.9 as the operating system. And here you have a photo of the workstation from Antigua, probably, right? And here's some screenshots from the FAZZT client and the Nova management app running in your ground stations, okay? Now, as we did with the DVB-S2 receiver, let's take a quick look at the procedure to install the FAZZT client on both Windows and Linux-based systems. And both procedures are available in the blog, and the links are also available at the Moodle page under the FAZZT, okay? And in your stations, FAZZT is already configured and running perfectly. However, in the future, it is possible that you need to install it in another machine for maintenance activities or during a possible update of the workstation, okay? Now, let me quickly open the blog and access the tutorials. Here you have the tutorial for Linux, right? Installing and configuring the FAZZT client on Linux. And as you may see here, you may download installation script from GitHub, this GitHub link, and you should put installation script, the FAZZT installer, and the FAZZT license in the same directory, okay? I'm going to show it very fast, very quickly, because you have this procedure available in the blog and also a summary in the slides. So, but this is just for you to have an idea of the process, what EEC did to install it in your workstations, right? And after you have downloaded the script, you run the installation script, install_fazzt.sh. It's a shell script, okay? And the script will run, right? And after some minutes, it will finish. And you will see a message here saying FAZZT installed. After the script, you need to run some additional commands to finish the configuration, start FAZZT client, right? And restart the HTTPD. And when you do that, if you access the browser and insert localhost or this address, port 4039/admin, you will see the GNC-A professional client main interface, okay? And here we have some steps for the configuration of the FAZZT client, as we are going to see later, right? So you have all the steps here. So basically, in this procedure, you are able to install the FAZZT client from zero in any machine you want. If you are, for example, installing a new station, okay? Well, now let me show you the procedure for Windows. And by the way, this is the procedure for Linux. Let me send it on the chat. And this is the procedure for Windows. And as you see here for Windows, you have the CD, and you need to access the third-party folder in the CD, also the SQL Express folder, and inside this folder you have a file, a bat file called install64. You just need to double-click, and the interface will install the database, right? And you just need to click most of the time in next, 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 and so on. Okay? Until the end. So in the end of this step, the SQL Server Express will be successfully installed, right? After that, you need to run the FAZZT Professional Client executable, right? Just double click at it, and you will see this window with some installation instructions, right? You just need to agree with the user license and insert the directory where you have your license file. Click Next. It will automatically detect the database. Click Next. And the FAZZT client will be installed, okay? And if you access, you see this little purple icon, an antenna icon in your system tray. You just need to right-click on it and select Start FAZZT, right? And it will say that FAZZT is running. And when you click at the admin, you see the main interface of the FAZZT client. So in both procedures, we are doing basically the same steps. However, in Linux, as always, we are doing with command line. And in Windows, we are dealing with graphical interface. But in the end, you have the same client installed, okay? So this is just an overview of the steps required to run, to install and configure FAZZT. Going back to the slides, for your future reference, we have a summary of the installation and configuration steps, right? And as we have seen in the online procedures, this is the summary for Linux. First, access the installer, right? The FAZZT installation script and your FAZZT license, right? You need to change the file permissions and run the installation script. And this script will install and configure database and install the FAZZT client, right? It will install the PostgreSQL database, configure the database for you, and install the FAZZT client. After that, you need to run some additional commands and run the FAZZT client, right? And here you have the same procedure for Windows. And I say that this is for your future reference, because as we are going to see in the maintenance aspect, it's a nice practice if for the future, in the future, if you can install both the Nova software and the FAZZT client in your laptops, at least those who are going to work with maintenance, right? Because with that, you will be able to check the status of your antennas, LNB, and receiver without needing to change anything in your workstation, right? And after you are sure that your antennas are well, your LNBs are working, and your receivers are working, then you start changing and investigating in your workstations, the data reception and data processing workstations. Okay, so that is why I would like you to have these reference slides available for you in the future. And for Windows, you need to run the bat script here inside the third-party folder, and it will install the SQL Server database. You need to wait for the database to be installed with the right configuration. After that, step number 3, install the FAZZT Professional Client. Wait for it to finish, right, and run FAZZT Professional Client as you see here, the main interface. And here I would like to stop for very, very important suggestion, right? And I really would like you to do this. Please make a backup of your license and installation files, right? I really suggest that every Met service should make a backup of the license and installer files for the future. It is relatively frequent that users need the license file installer again, for example, because they need to format their workstation or clean it or update it or use a better machine. And when they don't have a backup of the license file, they need to request this file to CANcast again. And if you send your license number, CANcast will provide the license again without any problems. However, to avoid this communication and need to wait, right? Keeping these files is very important. And the license files start with PC plus 6 numbers plus KCL, the .kcl extension, which stands for CANcast license, right? And these license files identify each user. As you may see in this screenshot, you have the user identified here. PC WeatherTech in your cases, because this is the vendor who assembled your stations, right? And you have FAZZT version 10.1, okay? And as I mentioned during the presentation about the disaster capabilities of the system, NOAA can select the specific stations in the community to decode specific data sets, which can be very useful for the disaster charter, for example, where users may receive commercial imagery. So this is another important reason to keep your license files and have your license numbers, okay? All right, so we have learned what the FAZZT client is. We have learned how to install it. Now let's see how to configure it. And as you will see, it is not hard. But before we see that, just remember that the third day, we have seen that in the station of the project, the receiver, the S300D receiver, is connected to one of the network cards of the data acquisition server, and that the IP address of the network cards in the workstations is 192.168.0.100. And you need to know this IP address for your configuration, okay? Once the FAZZT client is installed, you need to configure it. And the configuration is not hard, as we are going to see here. And you may find all these steps available in the blog, as we have seen, right? First, we need to tell FAZZT the IP address of the network card where the DVB-S2 receiver is connected to. And you may do that in the menu on the left side at Configuration, Channels, Channel Defaults, and Interface. You just need to select the IP of your network card. This is one example for my station, 192.168.0.23, but for your stations, it's 192.168.0.100, okay? Another option is selecting L, just selecting L. Apart from that, you also need to tell FAZZT where you want to store your data received by the system. You may do that at Configuration, Receive Settings, Virtual Path, Edit. And when you access the Virtual Path Edit, you may see here the physical directory where it is going to store the data. And by default, in a Windows machine, it is c/program files and cast fast incoming, right? But in the stations of the project, the ingestion directory has been configured by EEC to ESS, data, satellite, fast, okay? And the last step is configuring the so-called main channel. When we install it for the first time, this is the only channel you are going to see, the main channel, right? And it is accessed under configuration channels, right? And the main channel is the channel that is listed by default. And to detect the GeoNet Cast Americas channels automatically, you just need to click on Edit here and on Interface, select the default option or select the IP address of the network card where the DVB-ST receiver is connected to. On the first step, we have configured our network card as the default interface. So in the main channel, you may just add default, okay? And if everything is configured properly, after some minutes, you see that the GNC-A channels listed by the FAZZT client and the ingestion will start. And users will start to see the folders being created automatically in the workstations, right? Once you have configured your ingestion directory, as we have seen here in the station from SIMS, once you have configured the folder simply as GeoNetcast. And after the main channel was configured, all these folders, they are created automatically by the system. You don't need to create these folders manually, okay? That's if you are configuring, assembling a station from zero, okay? Now let's check some features of the FAZZT software. You may monitor the incoming files by clicking at Logs, Received Files. And you see here the exact time of the data reception for each file. Look here, dozens, hundreds, and thousands of files. You may see the exact time and date that you received them. You may also check here in Status if the files are being received without errors. Here, validated, okay? You may also check the statistics by broadcast channel, like in this example, where we see a graph of the channels being received. So we have here the channels as different colors, and here the colors being plotted, right? And here we have in the x-axis, we have the time and date, and the bandwidth usage in the y-axis. And as you may see here, some channels use more bandwidth than other channels because in the server side, there is a channel prioritization defined by NOAA. And the result of this prioritization is that some files arrive earlier than others. And if they are, for example, broadcast by the same time by the data providers, okay? So with that prioritization, NOAA and the system managers may select which files will arrive earlier in your stations. And as we have seen in the latencies during the first day, there are some bands that arrive earlier. For example, the legacy bands arrive earlier, the band from those 13. And if you look, for example, in the station from SIMS at GOES RCMI imagery, band 13, this is one of the higher priority channels, right? And if we look at the last file that it is available, right, it is from today, 1320 to 1330 UTC. And now it's 1340 UTC, right? And you see that this is a file from minutes ago. And now it's 1340. If we access this folder again in some seconds, right, we should have here and file from 1330 to 1340, okay? Okay. And finally, one of the most important information provided by FAZZT is accessed when you click at this white text here in the upper part of the window, where it is written CAN-CAST FAZZT administration and the name of the workstation, J0153 DPSG, in this particular station from Granada. And apart from showing the current files that are being received here, it shows some statistics for the last 24 hours. And this information is crucial. It is crucial because it shows the number of missing packets and the number of transmissions with errors. And if the percentage is too big, something is wrong with the reception. Something's wrong with the ground station. And that means that a considerable number of files are presenting errors or are incomplete, okay? And that could mean a possible interference. The antenna is losing the original alignment and for some reason, okay? So this is one of the parameters we need to check periodically, as we are going to see in the maintenance checklist later. And I would like to make a demonstration accessing the GNC-A Americas station from Granada remotely to show the FAZZT professional client in action. However, I cannot do it now because I still do not have the credentials yet. So I'm waiting for the credentials, and as soon as I get it, I will make a demonstration, okay? That's it for this first demonstration, and the objective of this slides is that you get familiarized with the FAZZT software, because first, you might need to install it in another machine in the future. And secondly, it provides valuable information on the quality of the reception, okay? Before we go to the next presentation, do you have any comments or questions about the FAZZT client? If you have any questions or if you do not understand any of these aspects, just let me know and send me a message on the chat box. Okay, now let me open my second presentation for today. Just a moment. And now we are going to talk about maintenance, which is one of the objectives of this training, right? And however, to talk about maintenance, first we need to understand how each equipment works, right? And now we have seen how the DVB-S2 receiver works, how the antenna works, how the LNB works, the bandpass filter, the feed, coaxial cable, and how the FAZZT client works, right? And now let's check more details of the workstations of the project. I'm sorry, I have opened the wrong presentation. It's the third one. Let me open the second one, right? Sorry. Before we talk about maintenance, we are going to talk about workstations. It's the last component we need to review, right? And we are basically going to review the specifications of both workstations, okay? And a workstation is basically a high-end, high-performance computer designed for use for technical and scientific applications. And they offer, in comparison to our PCs, they offer better performance on desktop computers, especially with regards to CPU and graphics, memory capacity, and multitasking capability, as we are going to see when we access the station from Granada. And on GNC-A Americas station, they are used to ingest, process, and visualize information uploaded by data providers. And in each station, we have two servers. First, the data acquisition server here, right? And the data processing and visualization workstation. The Nova receiver is connected to one of the network cards of the acquisition workstation, where the files are received just as the data providers uploaded them. And in the data processing workstation, the files are processed and converted to other data formats as needed by the visualization solutions. And here we have some photos of the workstations from St. Kitts and Antigua and Barbuda, okay? And as the operating system, we have CentOS 7.9 for both workstations. And on the data acquisition workstation, we have the Nova management application, version 6.3.15, as we have seen on the third day, sorry. We also have the Fast Professional Client version 10. And we also have custom scripts and utilities created by the vendor of the station, EC in your case. And these are created for resource management, data handling, and other important operations. Here we have the softwares running in both workstations, right? Here you have, in the data acquisition workstation, you have the Fast client running, right? The Nova management app running here, and the Proteus visualization software developed by EEC. Here you have the Proteus configuration interface and the Proteus visualization interface here and here, okay? And an important detail is that the data processing is done by the second workstation, but the visualization software can, as far as I understand, the Proteus software can be accessed in both workstations. Okay. Also, in the project recordings available at the Moodle page, you have a video of the workstation assembly with all the peripheral connections. Also, on the documentation made available by EC, they mentioned that each of the supplied workstation already have the ability to support 4 monitors, right? So as suggested by EC, you may add 3 monitors more in your data processing and visualization workstation. So it helps to explore the available product. And in our Moodle page here, you may access the recordings here at the additional resources, right? Here you have all the project recordings with site preparation, reflector assembly, reflector mounting, workstation setup, receiver setup, and software training, okay? And here we have the specifications of both workstations. On both machines, we have a 10-core dual Xeon Silver as the processor. And they are running in a CentOS 7.9 and 64 gigabyte RAM. We also have a 1 terabyte SSD SATA hard drive for the operating system and software in both machines. And 2 terabyte, 2 terabyte for storage in the data acquisition workstation, and 4 terabyte for storage in the data processing workstation, which is a very good amount of storage for a considerable amount of time. Okay, so as you see here, these are powerful machines, right? And as we have mentioned during the second day, there is a great variety of computers with different specifications being used by the community. And each user has what is available for them, or each user uses what is available for them in their countries and institutions, according to their processing and visualization needs, okay? And just to mention it again, GeoNetCast stations only need power for the workstations and for the DVB-S2 receivers. And the DVB-S2 receiver here, it provides power to the LNB here. So we just need to power the receiver, right? And in case of a power outage, the stations of the project are equipped with an UPS, which is an uninterruptible power supply, right? And it allows the stations to keep running for a period of time when incoming power is interrupted, as mentioned in the documentation provided by EC, right? Also, according to the specifications or according to the documentation, the UPS model of the project will allow the system to run for at least 30 minutes in the event of a main power loss, right? And as it is written here, it also helps to protect the equipment against line power fluctuation, which is during these events, right? So I really suggest that you make periodic tests to check the real autonomy of the UPS, right? And check if your institutions have their own generators that would serve to keep the station running, even when the UPS cannot provide power anymore, okay? And also for how much time that would work. This is something very important to check, right? Oh, and I had the plan to make a demonstration now and access the workstations and check the specifications, right? However, I still do not have the credentials, but I will do it for the demonstration for the FAZZT client and for the workstation parameters as soon as I have it, right? Probably after the break, okay? Now let's go to our next presentation. Now it is the correct presentation, the maintenance aspect, okay? And before we start the third presentation, I would like to make a pause and stop and ask you to have your Colab notebook with the NWP data processing examples ready for the next session, right? If you haven't done already, this notebook is available here in the end of the third day. And if you click here, you will be redirected Google Colab. And you will see this Colab notebook with more than 30 examples of NWP data processing. So as we have instructed in the third day, make a copy of it. And if you have done a copy, you don't need to do it again, right? You may use your own copy that you have created on the last session. You just need to create here at File, save a copy in Drive. So a copy of this notebook will be created in your Google Drive. So you are able to edit and you are able to change anything you want, right? And I have done that already in my notebook here. So what I have done is I have renamed my notebook to Diego underscore and the original name, but you may name it any way you want, okay? But it's important that you do it now and run steps number 2, which will install required libraries. Wait for it to finish. Run step number 3, which will download auxiliary files. Wait for it to finish, and then run step number 4, which will download GFS data from the Nomad server. In this, it will download data to this virtual machine provided by Google, okay? And as we have mentioned, this notebook uses more libraries because we see how to process NWP data, satellite data together, and METAR data. So we need more libraries. And it takes some minutes to run, right? 5 to 10 minutes. So that is why I really would like you to do it now. So when we begin the hands-on session with NWP examples, you are able to follow with me and make the changes with me, okay? And this is all online. You don't need to install anything in your machines. However, if you want to try your machines in Moodle, in the complementary activities, you have a link here called Processing NWP Data with Python Locally. If you click at it, you will be redirected to the blog, right? Here. And you have all the steps necessary to run these scripts in your computers, right? So here you will see how to install the tools, how to download data from the Nomad server, how to install an editor, in this case, Notepad++, and run all the scripts. The important detail is that some of you send emails to me saying that you already have successfully um, run Python scripts in your computers, but for the GOZAR procedure, right? And if you have done that already, you don't need to install the libraries again. You don't need to create a workshop environment again. You just need to execute and run the scripts, and your computers will be ready to run them if you have already done the first procedure, okay? And another detail is that in the GitHub page of the course, which you may access here, GitHub repository, you have the repository of this course here, and you have all the scripts demonstrated, and you have a folder called NWP. And inside this folder, you have all the scripts. So you may copy the content of this GitHub and run the script in your machines, right? Like this one. However, if you do not feel comfortable yet, no problem. You can run these scripts directly in the cloud. And as I said, in the first day, you have these two options to run in the cloud and running in your machines. And for the training purposes, running in the cloud is okay. However, in the future, if you want to create value-added products for your med services, you will need to install your software in your local workstations. Okay. All right. Before the hands-on, we have one presentation more. And now that we have seen how all the components work, right? Antenna, feed, filter, LNB, cable, DVB-S2 receiver, and the FAZZT client, we can talk about maintenance, and this is very important, okay? So in this third presentation, we will see a maintenance flowchart, which parameters to check in the case of a failure, learn how to use a satellite signal meter, check the LNB, the antenna, the workstations, and take a look at the suggested maintenance checklist. And in your stations are very good and very robust. The antenna has a big resistant reflector with a good survival wind speed, right? The antenna has a 6 inches pedestal encased in concrete, and the recommended foundation is also robust. The workstations are powerful. The LNB and DVB-S2 receivers are among the best available in the market, so it is unlikely that we will have problems, right, with our stations. But it is good to know what to do when your workstations stop, or if your workstations stop receiving data. And that's what we are going to see now, and this is also one of the desired learning outcomes as presented on the first day, okay? We already seen the functions of the configuration of each component of the ground station in detail and with real examples, right? And how each component communicates with each other. So the original files uploaded by the data providers of the system are reconstructed on the user side. So we have the satellite with all this data stream, how the files, we have learned how the files are reconstructed here in the user side. And now the objective of this presentation is seeing what to do, what we should do if the station stops receiving data for some reason, okay? And this is a suggested flow chart. So we have an idea of what to do in each possible situation, okay? And as you see here, when you notice a problem, first equipment you should check the DVB-S2 receiver, because as we have mentioned in the third day, the receiver has three LEDs or three lights indicating the status of the receiver. The power light here, the lock light, and the data light. And the status of the data light or the lock light will determine what we should do, okay? If the data light is on or the lock light is on and you are not receiving the files, right? That means that the GeoNetcast America's data stream is being detected, processed by the receiver. However, for some reason, between the receiver and the final processing stage of the FAZZT software, something is impeding the creation of files, okay? However, if the lock light is off, that means that the problem is either in the receiver itself or in the components before the receiver, like cabling, connectors, L&B, or the antenna alignment, or even a combination of factors, okay? So if the data lock is on, if the lock light is on, that means we could have a problem. For example, with the workstation, right? Like not having enough hard disk space to store the data. We could also have a problem with the FAZZT client, right? A communication problem between the FAZZT client and the receiver, for example. And if the data lock is off, the L&B could be damaged. The receiver itself could be damaged because, for example, a lightning surge, for example, or the antenna alignment may have been lost, for example, due to a very, very strong wind gust, okay? So in a summary, is the lock light, this light here, on? If it is on, the problem is here, right? If it is off, the problem is probably here, okay? All right. And apart from checking the lights at the front panel of the receiver, it's important to check more parameters using either the CMCS tool or the Nova Management app, right? As we have learned Monday. If you can't even connect to the receiver could be damaged, or there is a network failure. Your network card could be malfunctioning for some reason, as it happened before with some users. Or there was a change in the IP address of one of the network components. However, if you can connect to your receiver and the lock light is off, but you see a weak signal strength or carrier to noise values here, right? You could have a problem with the L&B and the antenna or the antenna alignment, or you could have some kind of an interference. And just to remember, the carrier to noise value here, which is 12.4 in this case, is a measure of the received carrier strength relative to the strength of the noise. So high ratios provide better quality reception, right? And accuracy and reliability. However, low values means that too much noise is introduced into the signal. And it may cause the receiver to be unable to differentiate noise from the GNC-A signal, okay? And here we have two examples, right, from a couple of stations, one from Panama and the other one from Costa Rica. Both of them have been configured correctly, had different results. On the left, it's from the antenna. They had the right configuration, but they do not have a lock, as you see here. Signal lock off, data lock off, carrier to noise not available, right? And the example from the right, it is from the University of Costa Rica. They had the right configuration. They had a signal lock, data lock, and a very good carrier to noise ratio. More than 14 dBs, and this is among the best ones I have ever seen, okay? And the problem from the station on the left, right, was the fine tuning of the antenna alignment, right, and the L&B scoop. But fortunately, they were able to solve the problem after some adjustment, okay? Another equipment that could really, really facilitate the verification, and I have one here with me, it is called a satellite signal meter, which is an equipment specially designed for this kind of analysis. And here we have some photos of these equipments being used by the community. And as you see here, there are many models of satellite meters, right? And the greatest benefit of having one of these is that you can measure the signal strength and signal quality independent of the rest of the station, right? Without the need of a receiver like the S300G, which is good because if the signal quality being detected by the meter is okay, the receiver is not locking the signal. That means that the receiver is probably damaged for some reason. Also, having a satellite meter allows you to make the verifications near the antenna, which really, really facilitates the job. Like on this photo here on the upper left, right, where our colleague, Maxi from Argentina, he connected a cable between the L&D and his satellite meter, right? And he's checking if the reception parameters are okay. And look here, he's near the antenna, right? So he don't need a DVB-S2 receiver and the workstations. And with that, you can make the adjustments on the L&D and on the antenna alignment and check the results in real time, okay? Also, having a satellite meter allows you to make these verifications alone, right? Meaning that a single person can check the parameters, right? And, and human resources is a problem. And I think some of you have these problems as we have here, right? And having technical staff, it's not easy. So a satellite meter allows you to make these verifications alone, right? Also, you do not need the NOVA receiver, which is usually far from the antenna. Another advantage of these meters, most of the time, in most models, there is an audio indication of the signal quality, like a beep, 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 that increases as the signal quality increases or decreases, right? So you can make the adjustment of the antenna and hear this beep and know if what you're doing is actually increasing or decreasing the signal quality, okay? There are many models of satellite meters available. Some of them are not expensive, some of them are expensive. And I use here one of these models, of these white models from this last photo here. And it costs around $50 only. So I really recommend having one of these for each station of the project, right? And this is my satellite meter. It's a very simple equipment, okay? Here, right? But you may ask, well, why couldn't I use the parameters from the NOVA receiver during the alignment? And the reason is that NOVA, the manufacturer of the receiver, doesn't recommend that, right? I have asked it some time ago, and they said it's not a good practice to use the receiver as a reference during the alignment. And for that, we need to use a satellite signal meter like this one, right? Of course, it is possible to monitor the signal strength with the NOVA receiver during the alignment, but apart from much harder, and you need more than one people, more than one person, it is not recommended, okay? And this is another model of satellite signal meter. It's called a BearDog, and it's one of the most advanced models available. And as far as I remember, some years ago, around 2018, this model has been used by CIMH to check the alignment, okay? And in a summary, it is written here in the yellow box, while it's not strictly necessary for deployment and maintenance, it is certainly a lot handier attempting to find a signal with the dish attached to your DVB-S2 receiver using the receiver software in your computers to test for a lock, okay? And another benefit of these satellite meters is that most of them may be used with batteries, meaning that you don't need a power plug to make this adjustment, which is very, very useful because usually near the antennas, you don't have any power plugs available, right? And this is the battery case of my receiver. So I just need to connect uh, this battery pack here, right? And it will turn on. Okay, I don't have the batteries here. That's why it is off, but just for you to understand how it would work. Okay. And by measuring the signal when you are near the antenna, guarantees that the signal strength and the signal quality is okay until that point. And another important detail, what is the difference between signal strength and signal quality? As you see here and here, right? High signal strength means that you are getting a strong signal from the satellite, but not necessarily for the transponder you are interested in. As we saw in the third day, there are many transponder available in the same satellite. However, a high signal quality means that actually you are receiving data for a specific signal configured in the satellite signal meter, which is the same one configured in the DVB-S2 receiver. And that means that during those verifications, you should always consider the signal quality, not only the signal strength, okay? And to get a good signal quality in the satellite meter, we need to be sure that our elevation and azimuth angles and the Allenby skew are properly adjusted, as we have seen in the second way, okay? And when you are aligning your antenna, or if you are readjusting it, if it for some reason loses the alignment, here are some steps that I suggest you to follow. And these steps really helped me, and I learned this sequence here after many frustrations, standing in the edge of many rooftops, okay? So first, you need to adjust the Allenby skew using an inclinometer, right? And it might be approximate, right? Secondly, you need to adjust the dish elevation using an inclinometer. It might also be approximate. Then connect your satellite signal meter. Adjust the azimuth until you get the highest possible signal strength. You will notice that when turning the antenna, when adjusting the azimuth, the signal strength will reach a peak. And then if you keep moving it and keep turning it, the signal strength will go down again, right? So you just need to keep the signal strength on the peak, right? And this is the most important step, step number 5. After you get the maximum signal strength, adjusting the azimuth, fine adjust the elevation until you see that the signal quality is increasing. Adjust it until you get the maximum signal quality as possible, right? So at step number 5, in your receivers here, you see this number increasing and increasing and increasing, the signal quality, right? And you usually recommend at least a quality of 70%. Here you have a bad signal quality, and here you have a very nice signal quality of 86%, right? And step number 6, after you get the maximum signal quality, adjusting the elevation, make the fine adjustment in the LNB skew again with a inclinometer until you get the maximum signal quality as possible, right? And after that, if your alignment is okay, and if the DVB-S2 receiver parameters are also as expected, then you need to check the FAZZT client. Check if you have any active alarms, check your files log, check if the IP interface is available, just to guarantee that you do not have a problem in your local network, okay? And by following the suggested flowchart of the procedure, sooner or later, you will find a cause that is impeding or preventing your workstation to receive data, okay? And before our group photo and before the break, here's one final comment I would like to make, which is we have artificial causes for interference, but we have also natural causes for interference. And this one is known as sun outages. And in the past, some users reported a daily periodic decrease in the signal to noise ratio, right, of their stations. And that caused reception losses sometimes, right? And these are 10 to 20 minutes decreasing, and it happens during the sun outage. And this is a natural phenomenon, right? And let me just quickly read what Intelsat says about this phenomenon, right? Here it is. Geostationary satellites are stationed over approximately 36,000 kilometers from the Earth and located over the equator. Given the equator is offset by 22.5 degrees, the sun here aligns directly with satellites and the receive stations twice a year, once in spring and once in the autumn. And this event is called a sun outage. And it is also known as sun fade or sun transit. And the heat emitted by the sun is an intense source of noise, right? And that noise is called the thermal noise. And when the sun is aligned perfectly with the satellite and with the antenna, right, noise increases. And it may increase above the satellite carrier signal noise, and this may cause a temporary loss of reception, okay? So that's what Intelsat says. And here we have an example from the Milton, which is one of the GNC-A users from Brazil. And he created a daily signal to noise ratio plot between, in this example, between September 9 and September 13, between 12:30 and 13:30 local time. And that's the time slot expected for the sun outage to occur. And as you may see in this graph here, during the sun outage, he had some a decrease in the signal to noise ratio, right? And as you may see here in this photo, the sun is perfectly aligned, as we see here in this illustration, the sun is perfectly aligned with the satellite and the antenna. And that is why the shadow of the feed is perfectly in the middle of the dish, right? And as you may see, the duration of this event was approximately 20 minutes. And for this particular station, it caused a 10-minute break in the reception a day, during one day, right? And it is totally possible to predict when this event will occur. And if you want to predict it and when it will occur for your site, you may use this link here, okay? And to finish, I just would like to show you this maintenance checklist. And when I have the credentials to access the station from Granada, I would like to make this, to fill this table with you, so you may understand the critical parameters you need to monitor. Okay, now it's time for the break. And before the break, we will take a group photo, right, Cassian?
Yes, I'm here. Everyone, if they can turn on their cameras and position themselves. Rebecca, would you be taking a picture? Or you want me to do it? If you stop sharing and we go to view, gallery. Thank you, everyone. Diego, I think you have to stop share for a minute.
Okay.
Give me a minute. I'm still seeing a screen. I'm not sure why. So I'm not getting everyone in the picture.
When you click at these little squares, you can see everyone,
yeah, okay, hold
right?
on. Yeah, but I'm still seeing your screen for some reason. Hold on 1 second.
Oh. Yeah, try it now.
There we go. Perfect. Okay, so Elvis, Maya, Farah, Namuel, Sisney, Eugene, we need your cameras on, please. Thank you. It'll just take a minute. Micah, Miss Thomas, sorry. Farah. Thank you, Eugene. Sisney and Farah and Elvis. Okay, if not, because you don't want to hold back the break. All right, so everyone, hold on. I got my print screen there. Okay, everyone look at the camera. 1 second. And smile. And print screen again. Rebecca, you taking as well?
Cool. No, I was just smiling.
Smiling? Just take one just in case mine don't come out. Looking very sharp, Leonard. Thank you. All right, so let me just check these really quickly. Ready, camera. Okay, document. Okay, we can all go on break, and if there's an issue, I'll do it right after the break again. Thank you very much, everyone.
Thank you. Thanks, Kathy, and thanks, everyone. And we will be back at 10:40. Thank you.
Thank you.
Hello, everyone. Let's return from the break. And after we go to the second part of the NWP hands-on, in the Moodle web page here, just a moment. In the Moodle page, in the end of the 4th day, we have 2 assignments, right? And this is the first one, GeoNetcast America's maintenance checklist, okay? And when you click at it, you'll see this window, and you will be able to download this spreadsheet, this PowerPoint with this table, right? So you may click here, download that file. When you open it, you should see this table, okay? So, and here the title, you may insert your site, for example, Granada, and you have all the parameters that are crucial to check for you to understand the status of your ground stations, okay? So the idea of this exercise is that you understand how you may check these parameters in your ground stations. So if possible, I would like you to try, for those who already have an active ground station, I would like you to check these parameters, insert the status here on this spreadsheet and this table, and upload the table to the Moodle page. As soon as I have access to the station from Granada, we will do this together, okay, as a demonstration, right? As soon as I have the credentials, but this is one of the exercises, okay? The other one is here, creating advanced plots and animations for any time interval, right? When you click it, you see this window. You will see a link to the GeoNetcast America's blog and some instructions of what you need to do. Okay, if we open the blog, you will see this page, creating advanced plots and animations for any time interval. And if you are accessing for the first time, it will ask for a password, and the password is workshop. So by the end of this activity, we will be able to create more advanced plots with Python, and more importantly, we will be able to animate these plots with a nice web interface, okay? In the Python script, you will also see how to download information, plot and animate images for any time interval since the launch of Go16, right? And if these files are available in Amazon. And as a prerequisite for this activity, right, participants need to finish complementary activities available in Moodle, right? That is how to run the Python scripts locally. Because in this activity here, you will need the tools installed during the complementary activities, right? Like Conda, like having the virtual environments and libraries installed, right? So as you may see here, you will need to click at this link and download a zip file called animation, right? You will download this file called animation.zip. And inside the zip file, you have other folders, as you see here. And in each one of these folders, you have some files. For example, inside the color tables folder, you have some color map files. Inside the HTML folder, you have a basic web structure for data visualization. Inside the logos folder, you have logo from CIMH in this example, in PNG format, right? In the output folder, you have the PNGs that will be generated when running the script. In the samples folder, you have the netcdf samples that will be downloaded by the script. The script folder, you have the scripts that you will use to download, reproject, plot the images for this animation. And finally, in the shapefiles folder, you have the shapefiles used to create the plot, right? And finally, when you click at myanimations.html, and let me open it here. So I will create a folder in my computer right now called my animation, for example. Here, I will paste this zip file inside this folder that I have just created, and I will unzip it. Okay. Inside this folder called animation, this is the structure I have. Okay. As we have seen in the procedure here. Color tables, HTML, logos, output, samples, scripts, and shapefiles. Okay, if you click at myAnimation.html, this is what you see. At this point, please note that we didn't run any scripts, nothing. You just download the zip file, extracted the zip file in your machines, and that's it. Okay. And then when I click this HTML link, you see this animation interface. And here at the blog, you have a description of each one of these buttons. Stop the animation, start the animation, etc., etc. Right? Right? Here, for example, if I click, sorry. If I click at the play button, I will see an animation. And in this case, from July 29, 2020, okay? From 0 to 24 UTC with an interval of 1 hour between each image, okay? Right? If I click stop, it will stop. If I click play, it will play and run the animation. And I can also change the frame by clicking here or here, as you are seeing. Okay. I can also increase the animation speed. So when I play, it is much faster. Okay. I can also change the animation mode like this, back and forth. Okay. And I can also zoom in. Okay. And if you would like to check a particular region. Okay. Also, there is a button called draw. If you activate it and click, let me pause the animation, and click at each one of these colors, for example, yellow, you may draw in screen. Okay, change the color, draw, change the color, draw. Okay, and if you click on clear, all the drawings will disappear. Okay, let me take the zoom out. And here you have logo from CIMH. And here you have some labels with the name of each state participating in this project. Okay. And here you have an image of 13, the 10.3 micron band. You have a legend, a title inside the plot, right? Not outside the plot like we are doing in the procedures. And here you have a scale, 1,000 kilometers. Okay. So this is a more advanced plot, and this is a web interface and web animation interface and HTML interface that you may use in your services. I know that some of you, like Eugene or Wayne, you are developing images, you are developing websites, right? And this is an option for you to use. You may use it for free. It's available for use, this HTML structure. And in this activity, right, objective of this activity is that you learn parameters you need to change this animation, right? So in this example script, which is available inside the scripts folder here, animation scripts, there is a script called script animation. Okay, and here it is. It is big, right? It is big. However, there is a session in the beginning of the notebook of the script that I have called user input begin, user input end. And these are the only variables you need to change during these activities. If you want to change, for example, the region of the plot, the band, the initial date and the end date, and the interval between the images. So by changing this and running the script locally, that is why the prerequisite is to have installed the tools in your computers. And I know that some of you were able to do that, right? By changing these parameters, you will be able to create a whole different animation for another region, for another band with another color scale. And that's the idea, right? And I would like you to try changing this script, which is called script animation, right? And change it according to these parameters here, right? We will open this script, change these parameters, right? And here we have an example how your script should look, right? And then run it again. Also, if here inside the scripts the logos folder, if you put your logo here in a PNG format and call it my logo.png and overwrite this logo from CI and H, your logo will be visualized here in the animation. Okay, so that's the idea of this assignment, especially for your technical staff that is working with web pages. If you manage to understand this exercise, you will see that you will be able to use this basic HTML structure in your web pages in the future, right? Which will make things much easier for you, okay? So this is proposed, and in the 5th day, this Friday, we will review this activity and learn what the script does step by step and how this interface makes the animation, okay? And this should be your result. When you manage to create the animation, this should be your result, okay? But this is for the suggested date. If you want, you may change the parameters of the script to any time interval you want for any specific severe event you want and create your animation just to practice. And then this Friday, we will review how to do that. Okay, so these are the 2 assignments we have in the end of the 4th day, okay? Now let's go to the second part of the NWP, hands-on. Just a moment, let me find the presentation. Here it is. In the last day, we started the NWP hands-on. We have learned how to list the variables available in a grip file. Independent of the model, you may use the same concepts for GFS, for ECMWF, or WRF, and others, okay? We have learned how to make a basic plot, read the metadata, add a title, a color bar, a map, and a shapefile. And as I mentioned, the objective of this activity is that you understand what is needed to create your own plots, like in these examples created by my meteorologist colleagues from NPE. They have attended a similar training in the past, and after practicing for some time, they were able to create very nice images like the ones you're seeing here. And these ones are created by my colleague Regina to analyze a tropical storm in this example. Here are some other plots created by my colleague Marcos. Here are some other plots created by him to study the intertropical convergence zone. And here are some other plots created by Diogo, which is another colleague, meteorologist here from CPTech NP. And that's the idea. Considering that you have access to digital files like the ones received in GeoNetcast Americas, for example, or downloaded from the cloud, or downloaded from any other means, you are able to produce products to your Mac services in the near future, okay? And on the last day, we stopped in script number 6, right? In script number 6, we start learning something completely new and related to NWP data, that is plotting contours and labels, right? Let's review our script number 6. And until this script, we were plotting the data as it is, rows, columns of pixels, and we were able to see how low resolution these examples were because we were working with half-degree kilometer resolution files, right? So in this example, plot contours, right? And here are the instructions used, as we have seen on the last day, right? First, we need to define the minimum and maximum values of our contours. And we have created a couple of variables called data min and data max. And in this example, we have -20 to 48. And in this example, we have an interval of 2 degrees, right? And to plot the contours, we have seen that we may use basically 3 instructions. The first one called contour F, meaning that it is a field contour. The second called contour, meaning that it is an unfilled contour. And the third one called C label. And these are the labels of my contours, okay? And I need to pass some arguments for these 3 commands. And these 3 commands are commands from the matplotlib library, right? In the field contours, I'm passing the longitudes, the latitudes, data I want to plot, in this case, 2-meter temperature, the color scale, jet, and the levels. In this case, between -20 to 48, with an interval of 2 degrees, right? To the unfilled contour instruction, I need to pass longitudes, latitudes, 2-meter temperature, and I also select a single color in this case, and in this case, I'm plotting the contours as white, right? And the line widths of my contours and the levels, because these are the same levels of the field contours. Finally, in my C label command, I'm informing, right, the image that I would like to label, in this case, my unfilled contour, image 2, right? And I set the inline parameter as true or false, meaning that I want the underlying contour to be removed where a label is placed, right? I also set inline spacing as 0, meaning that I don't want any spaces between the labels and the contours. The size of the labels, the format of the labels, and the colors of the labels as black. And in my color bar instruction, I refer to the field contours, one that I am using the color map, okay? And as a title, I just put 2-meter temperature and the other instructions we have already studied on the previous days, okay? And this should be the result on the left here. I'm not seeing the data as a simple plot anymore, like we did with the inShow command, but I'm seeing my data as contours, which is appropriate now. Also, in many cases, we want to show only the unfilled contours, and that's very easy, as we are going to see. I just need to delete my contour, the field contour command, and plot only the unfilled contours applying a color map, okay? And here we have a couple of examples more for South America with field contours and unfilled contours on the right. And these examples and these concepts will be very useful in some cases, like in this one, right? Where we are plotting the pressure reduced to the mean sea level, right? And the thickness between 500 and 1,000 hectopascals, right? And these are unfilled contours over an ABI image, right? And here are some quick modifications. We can change the appearance of the contour and the appearance of our labels very easily. And let's make a test in Google Colab. And I really want you to try to make these changes with me. Let me close some of the windows I have here. I have many tabs. Just a moment. Okay, here I have my notebook. It is also available in Moodle page, right? And in the last day, we have run script number 1, knowing the available variables in a grep file. And you see that when you click at this, you see all the variables being listed. And for this particular GFS file, we have more than 1,000 fields, okay? Then we created a basic plot. Then we read the metadata, converted to Celsius, added a color palette, legends, and titles. And this is the result. Not very nice yet, right? And in our fourth example, we learned how to overlay maps with Cartopy, okay? In our fifth example, we learned how to add shapefiles. In this demonstration, I have added a couple of shapefiles, the states and provinces and the marine regions, just to exemplify, okay? And now we have this example number 6, plotting contours and labels, okay? And this is the script as the way it is, right? Jet color map, white unfilled contours, and blue labels. Let's change the appearance of this plot. First of all, I'm going to change the color map from jet to matplotlib color maps. And you know, for this example, I'm going to use this one, CMR map. Okay, from black to purple to red to yellow. CMR map. CMR map. I'm going to change the thickness of the unfilled contours to 0.5, for example. Now you change the labels from blue to black, right? Let us see the result. The script is running. And this green arrow shows where the script is being executing, the specific command line that this script is running right now. And here you have, right? We have these black labels, the new color map, and I have increased the thickness of the unfilled contours. Okay. Now I will reduce the label size to 7, for example. I will increase the inline spacing to 5. And you change the minimum and maximum values of my color scale of my intervals from 48 to 40 and minus 20 to 0. Okay. Let me put 1 degree of interval instead of 2. Let's run the script again. That's what I did. From 0 to 40, interval from 2 to 1, I have changed the font size of the label, right? As you're seeing here. And this is the result. And as you see, we have more contours because my interval now is 1 degree, not 2, right? That is why we have here 25 and 26, because I have increased my interval to 1 instead of 2. Now I'm seeing more colors of my color map because I have changed the minimum and maximum values to 0, between 0 and 40 instead of -20 to 48. Okay. Now let me change the color map again to, for example, rainbow. And run the script again. Let's see the result. And here it is, the new plot with the new color table, right? I can change, let me see. I can set inline as false, for example, as 0. Let's see the result, okay? If I set, and let me change the contours to black instead of white, and the labels to red instead of black. And you see that instead of having the labels, between the field contours, you have them in the upper part of the unfilled contours. Can you see it here? Now they are over the lines, right? So this is just to exemplify that we may change any aspect of the plot, right? Another thing I would like to show you is that, let me return to the initial state of the script. I would like to show you that it is possible to plot only the unfilled contours. And let's see how we can do that. So I'm going to comment the instruction with the filled contours. And in my contour instruction, I will add a CMap instead of a color. If I change the color parameter to CMap, right, I will plot my unfilled contour not as a single color, but as a gradient, as a color map. And that is useful sometimes, as we are going to see, okay? Let's see the result. And here you have, but as you may see, it's not that great. So let's increase line width to 1.5, for example. And let me change the colors to black again. Let's see the result. And here we are, with these print commands here, we are printing in the terminal the analysis date, the forecast run cycle, the forecast time, and the valid time. Okay, and here you have, right? Only the unfilled contours with an interval of 2 degrees with black labels, right, over my map. and I have a black map, and I have red states and provinces, a title, and the valid date. And this is for May 10, this is for today, okay, 0 UTC. Okay, so these examples are just for you to see that you have total control of the information, okay? And that's the idea. Now let's go to our script number 7. And in this script, we will learn something very useful. We will learn how to create custom color palettes. And to do that, we will use the commands inside this blue box here, right? As it was mentioned during the goals are hands-on, Matplotlib has many standard color palettes, right? Or color maps, as they are called. However, when you are working with WP data, for example, or satellite data, sometimes these color maps are not sufficient or are not appropriate for your purposes, okay? And in this example, we will show you how to create a color map from 0, right? And to exemplify that, we will see how we can replicate this color palette here, right? And this is not available in the standard Matplotlib color map. So this is just a random color, random web page showing a field, right? Mean surface temperature in this case. So we will replicate this color palette. However, the idea is that you understand that any color scale you see around the internet may be used in your script. And let me send this link in the chat box, so you may take a look at this page, but let me open it here as well. And here you have, this is a random color scale that I have found around the internet, and I want to use exactly this color scale here, but in my plots. Let's see how we can do that. And to do that, we need to retrieve the so-called hexadecimal values of each one of these colors and add these X values to our script. And to do that, right, we need to enter this web page here called image color picker. Add the link to the web page that we have the desired color palette and retrieve the colors, right? Let me make a demonstration. I will open this web page called image color picker, and you have that on the chat window, right? And here you have a default image. If I click here, or here, or here, you will see the X values being shown here, okay? If I click to add use your image and select website URL, right? You may insert any web page here. If I copy and paste the web page with the color scale I want to use, here it is. It will show you that web page, and you will be able to click at any point here, 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 etc., and retrieve the X files, the hexadecimal values for that particular color, okay? And after I have copied these X values, I may use them in my script. So that's how you do that. That's how you create a color scale from scratch. And let's see the next step, right? And here I'm saying that, when I click at a particular region, I will see the X values here, okay? And in my script, the first thing I need to do in my libraries block, I need to import the general matplotlib library, right? Because the matplotlib library will provide some functionalities for me to create custom color tables or color maps, okay? So that's the only thing I need to do in my libraries block, okay? And in my plot configuration block, The only thing I need to change is this here, right? I need to create a list of colors with all my X values retrieved from the web page. So in this case, I have 1, 2, 3, 4, 5, 6, 6 times 4, right? 24, 25, 26, 28, 29, 31 values I have retrieved from that page, okay? And I need to give it a name for this list, right? In this case, I have called it the list colors, but you may call it any way you want, right? And between the brackets, just add each one of these colors separated by a comma. And after creating the list, create a matplotlib color map with the colors command, right? Using the listed color map command. And I pass to this function my list, which is called colors. Here, I pass it here. Okay. Also, I need to inform which colors I want for the values under my minimum value of the scale. And the color that I want over my maximum color of the scale, right? As we are seeing here. Here I have values between brackets. Here, the value over and the value under the minimum, okay? That's what I'm doing here, over and under, list of colors. So with this 4 commands, I can create a color map from 0, okay? And I have called this color map simply CMap. I have my Ctrl F instruction, I have used it. CMap is equal to CMap because I have called it CMap, but I could have called it my CMap example, etc., etc., etc. So I just need to use the same name here. And this should be the result. In the left, we have the 2-meter temperature plot with the same color scale of the example web page, right? And I can replicate the color scale from any web page, like in this example from the right. This is an example from our web page here at NPay, right? So I have accessed this web page here and retrieved the color scale used in this particular field, right? But if you enter, for example, our web page here, and here I have WRF and I have BAN, ETA, and BRAMS, which are regional models, right? Regional models developed here where I work. And I may select any variable I want. For example, precipitable water, which uses this color scale here. And I may copy the colors of this color scale here, right? If I insert this image in the color picker, I can replicate this color scale in my script, okay? Just let me make a demonstration in Colab. Here we have script number 7 in your Google Colab notebooks. And if you click at the play button, this is your result, right? The color scale we have replicate from this web page. But for example, I have another color scale here. Let me just comment lines with the old color scale and uncomment the lines with the new color scale. I want to use that I have replicate from my site here, from our web page, and let me send these instructions in the chat box. If you paste these instructions from the chat box in your Colab notebooks in script number 7 and run the script, let's see the result. These are the metadata, analysis, model cycle run, forecast hour, and 0 UTC. And here you have the same variable plotted with this totally custom color scale. Okay? So you have total control of your data. All right. And as you see here, knowing how to create a colors map from 0 is very useful. And here you have some examples of satellite data that I needed to create custom color maps because they were not available in the standard matplotlib color maps, right? Here I have some derived products from goals like cloud height, cloud phase, TPW. Here's the total ozone product from JPSS, the total totals, derived stability index from goals, surface wind speed from GCON satellite, and the blended TPW product that we have seen on the first day with panoply. So this is very useful. And if you like me to try to replicate the color scale from any model plot during this training, just send me a link of the web you want, and we can do that as a demonstration, okay? Now let's go to our next script. And if you have any questions, just send your questions in the chat box, okay? And here in script number 8, we will learn how to smooth the contours. And we have seen that we are working with GFS files with half-kilometer resolution. You may download higher resolution data sets from Nomads if you want. And you can also work with much higher resolution outputs from other models, right? However, in some cases, the low resolution of your data could be evident in the plots. And in some cases, it's useful to smooth the contours. And that is what we are learning to see how to do now, okay? In comparison to the previous script, we have added commands on this blue box here, okay? And look that it's not very big, right? And as we have seen earlier, it is possible to check the dimensions of our data with the shape command, right? In this example, to check the dimensions of my data, I can use tmtmp, 2 meter temperature, which is the name of the variable I have created, dot shape. And in this example, the dimensions of this particular data set is 81 rows by 121 columns. And if we reduce the region even more, right? Like in this example, where I have selected the longitudes between minus 85 to 60 and between 10 to 25, right? I have an even smaller data set with 31 rows by 51 columns. And the low resolution data is evident in some parts of my plot, like here, for example, right? You have these spikes in this example, okay? And to smooth our plots, we will use the zoom command. Of the zoom command of the image module of the SciPy library. And SciPy is a very useful library. It provides many algorithms for optimization, integration, interpolation, algebraic equations, differential equations, statistics, and many other classes of problems. And in this case, we are just going to interpolate our data and increase the size of the data sets we have, right? Just as an example. And as you see here, with only a few lines of code, we can increase the size, we can increase the dimensions of our 2 meter temperature, latitudes and longitudes matrices, right? And we need to pass only 2 parameters. First, variable you want to zoom in or interpolate the data. Also, zoom factor. And in this example, we are using a zoom factor, right, of 3. meaning that we will increase the size of our variables by 3, applying an interpolation. And if we look at the documentation of this function, here, you see that it uses the spline interpolation of the requested order, right? So in this example, we're just doing that, right? And after we apply the zooming with this function, the size of our data will be multiplied by 3, right? And before the interpolation, we had 31 rows by 51 columns. And after the interpolation, we had 93 rows by 153 columns. That is not strictly necessary when dealing with NWP data, but you can do that if you want. And not only with model data, you can do that for any data set you want. If you want to have a higher resolution zoom, right, in a particular image we are producing, you may use this function. Of course, consider that the pixels are being interpolated, right? And here you may compare plots before the interpolation and after. Look how it is smoother in the second case, okay? So that's what you see in script number 8. And you may run it in Google Colab. It is called smoothing contours. And here, you may change the interpolation factor in order to test, okay? That's our example. And here we have the result for today. This is for, no, this is not for today. This is for May 7th, which is the last time I run this cell, 0 UTC. Okay. Now let's go to our script number 9. It is a very nice script. And here we will learn how to work with multiple files. So we are able to process many files sequentially and create an animation with the plots and generate a GIF, for example, right? Until now, we have worked with a single input file and generated a single plot as the output, like in this example, right? So far, we have only worked with a single file and generating a single output. As you see here, the script does this from the beginning to the end. In the end, you create the PNG, right? However, in script number 9, we will use a loop, a for loop, to repeat the processing as you are seeing here, as many times as needed, right? Creating the number of PNGs we want. So in this example, we have these libraries, these blocks of code. The libraries block with our libraries, block where we configure the loop, how many times we want the loop to iterate and other information, right? The beginning, the end and the interval. And we have the loop here in gold or yellow with the instructions that will be repeated X times. And inside the loop, we have our blocks that we are already accustomed to, like the data reading and manipulation block and the plot configuration block, okay? And as the output, we will have 9 PNGs from 0 to 24 hours, every 3 hours, okay? Let me run this cell in Colab because it takes a while to run, because it needs to process 9 files, 9 images. So here's the first image being processed, right? So I'm processing this file here with the forecast hour 0. I have created this first plot. Now he's processing the second file, and he will create another plot for 3 a.m. UTC. And Here it is. So this script, you generate 9 PNGs using the same script. And how can we do that? Let's see. Here we have our libraries block, right? As we have done during the GOZAR data processing, we will import the OS library, the operating system library that allows us to have an interface with our operating systems using a Python script, which is nice. And in this example, we will use this OS library to create a folder called animation, right? And we will store our plots inside this folder, our PNGs, right? In our next instruction, we select the extent just as we have been doing until now. Minimum longitude, maximum longitude, minimum latitude, maximum latitude. Just be sure that this extent is under the maximum boundaries of the data you have downloaded from Nomads, or that is under the boundaries, inside the boundaries of the data you have in your GeoNetCast Americas station, okay? And in the next 4 instructions, I will configure my loop here. We will create a variable called file. And I have the name of the GFS file naming convention, which is GFS, the cycle runtime, 0Z, the resolution, and the forecast time, F plus 3 numbers, as we are seeing here, right? F0, F3, F6, F9, etc. Because this model output here is produced for forecast times with a step of 3 hours. And I will remove, look here, I'm not inserting the last 3 digits in my variable name, right? And I will use this loop here to change the forecast time in my file name, right? In each iteration of the loop. After that, I create 3 variables. Our init with the starting time of our loop, our end with the ending time of our loop, our last file, and our int with our interval. And that is why I have 0 as the start, 24 as the end, and 3 as the interval, because I want to process the forecast times between 0 and 24 every 3 hours. Then I start my loop, right? Saying that for every hour between the starting hour and the end hour, I want to increment my interval 3 hours, right? Between 0 and 24 plus 1, I would like to increase 3, right? And I'm summing 1 to my end hour because in Python, for loops ignores the last value of the loop. But I want to process the forecast time number 24 also, right? That is why I'm adding 1 here. So the loop will also consider my last file, my 24-hour file, right? After that, I will create a grib variable, a variable called grib, with my file name plus the 3 digits corresponding to the forecast hour. And in every cycle, this hour will be incremented or increased between 0 and 24 every 3 hours. However, as we have seen in the 3rd day of the training, the GFS file convention have 3 digits as the forecast time. So here we are using the zfill command and have 3 digits independent of the number of my hour, less than 10, more than 10, etc. I will always have with this command here 3 digits. And with that, I will reconstruct my file name according to the loop. After that, I just confirm with the OS library if that file exists, right? Because for some reason, maybe one of these files are not available in Nomads and they are missing, and I don't want my script to display an error, right? So if the file doesn't exist, I do not process the file. But if it exists, I process the file. You may see that this OS library here is very useful. We can create folders, delete folders, and we can also check if a file exists. And if the file exists, we process the file. The file will exist because in the Colab notebook, step number 4, we have downloaded files. In step number 4, we have downloaded files between 0 and 24 hours. Every 3 hours, they are downloaded using step number 4. That is why in my script number 9, I was able to look here, one image per forecast time. So I'm running through an entire day, right? From 0 to 0 again, plus 24, right? And this is for today, May 11. This is for tomorrow, right? The valid time, May 11, 0 UTC. Starting from today, May 10, 0 UTC to 3 a.m., 4 a.m., 6 a.m., 9 a.m., 12 a.m., 15 a.m., 18 a.m., 21, and 24. Okay. Just to exemplify the Z-field parameter, for example, if I have a number, my number, equal to, for example, forecast time number 3. If I print it as it is, my number, I will get a 3, a single number. However, if I plot my number dot Z-field 3, I will have my number with 3 digits, and that is what I have done in my script. Okay, Z-field 3. If my file exists, it will process the file just as we have been doing until now, right? And with that, we are able to process many files using a single script. 9 files in this example. The only difference is that in the instruction that we create the images, here, right? In the file name, I'm saying that I want to save the PNGs inside the animation folder, and the files will be called image_loop_forecast_hour.png. But this is just an example. We could call it any way we want. Also, I have a couple of parameters here. Bbox inches tight and pad inches 0. And with these parameters, I'm just saying that I want to remove additional blank spaces in the image boundaries. So my PNGs will only have the plot itself without a white border. And that's because here, the fixed size, we are just saying that we want an 8 or 8 inches plot, right? But we do not know if that's the real size of my plot. We have just inserted these numbers here. So with these parameters here, Bbox inches and pad inches, I'm just removing the exceeding white spaces. Let me see if I have it locally here. See, VLab, NWP, Python, NWP. And if you, for example, look at image number 7, look here that I have white spaces, right? Here, because I have inserted any 5 dimensions I want, which not exactly matches the dimensions of my plot. So with those parameters, I'm just saying, hey, please remove these white spaces from my plot, right? And this is what I have in my Colab notebook. Okay. And with that, we have 9 PNGs, as you see here. But we also want to create an animation, right? We don't want these images separated only. We want to create an animation. In this case, we will create a GIF file, right? And to create an animation, we have our script number 10. And considering that we already have all the PNGs available inside the animation folder, script number 10 is a very simple script, right? And to generate a GIF file, we will use this library here, image.io, right? And if we access the image.io documentation webpage, here it is. We will see that image.io provides an easy interface to read and write a wide range of image data, including animated images, right? So in our script number 10, we import image.io library. In our next instruction, we create a list of files called files, in this example, inside brackets, right? And I have all the PNGs I have generated the previous script, from image loop 0, image loop 3, image loop 6, until 24. And after that, I have a for loop in which I append, right here, images append each one of these PNGs to my GIF file using the image.io read command, right? So here I'm listing the images. Here I'm appending the images to the GIF. And with the last instruction, I finally create the GIF. And I give it a name, any name I want. In this case, animation.gif. Okay? And I can pass some parameters, but the only parameter I'm passing here is this one, frames per second. And I put 1 frame per second, meaning that I want my animation to show one image every second, as you see in this animation here on the left side, on the right side. And a nice thing about this library is that you may use it to animate any images you want, right? You may create a GIF with satellite images using the same instruction, right? And that's our script number 10. And if we go to Colab, I will run script number 10, but I will reduce frames per second to half. So, sorry, 2. So I will show 2 images per second in this case. Okay, opening the GIF. And here you have 2 images per second. From today, 0 a.m. to until tomorrow, 0 a.m. in this case. Okay, and I can change it to 5 frames per second. Opening the GIF. And here you have it. Okay, so this is a very nice library to create animations, right? We are not going to see script number 11 and 12 during this training. We will jump to our script number 13. However, for these scripts we are not going to see today, you may run them in your Google Colab notebooks and use them use this slide deck that is available in Moodle as a reference. We will be jumping some scripts, but the idea of these demonstrations is that you know the possibilities of working with digital files like grip files. And if you need to use any of these concepts in the future, independent of the model, GFS, ECMWF, etc., you can use these examples as a reference. And just for you to know, in script number 11, we learned how to make calculations inside loops. And we also learn how to create multi-plots. That is more than one plot in a single image, right? And in this example, we learned how to calculate the maximum, minimum, and average temperatures for 24 hours for the same pixel, right? And just to show it quickly, we have a loop, just as in the previous example. And inside the loop, we read each file. However, in each cycle, we calculate the maximums, the minimums for each pixel. At the end of the cycle, here, we calculate the average at the end of the day. And then we proceed with the plot configuration. And in the plot configuration, in this case, I say that I want to create a multi-plot with one row for 3 columns, right? One column for the minimum, one column for the maximum, and one column for the average, right? And we also learn what you need to change to create a multi-plot. And here we have the configuration for the first plot, for the second plot, and for the third plot, right? And this is the result for our script number 11. We are not going to see the details today. We have a single PNG, right, with multiple plots, minimum, maximum, and average in this case. And learning how to create multi-plots could be useful sometimes when you need, for example, to compare information, or when you need to provide information to your downstream users in which they need to compare multiple images in the same image, right? But this is not our priority today. We will also not see script number 12, but for you to have an idea, in this script, we learn how to plot the precipitation and the accumulated precipitation, also in a multi-plot, right? And the idea of this example is that participants learn how to read a given variable has multiple indexes, like here, 1 instead of 0, as we have seen on the previous day, right? Because the precipitation field is a little bit different from the others because inside the same variable, you have different time intervals. So you have accumulated precipitation between 0 and 12 hours, 12 and 24, and so on. So this is the objective of this example. And as we have done in the previous script, we show how to create a multi-plot. And here's the configuration for the first plot, the configuration for the second plot. This is the result. Instant precipitation rate on the left and total precipitation forecast for 24 hours in the right, okay? So these were the first part of the script I would like to show you, right? And in this second part here, we have other examples with more advanced concepts. And today we will not see all of them because we have our priorities, but in the slide deck that are available, you may use them. All of them are explained for your future reference, right? And before moving to script number 13, we have some slides explaining how to download data from nomads using Python scripts, right? Learning how to do that could be useful for you in the future. With Python, you can download any information from the web automatically, as long as you know the URL or the address of that file. And in this example, we are downloading grep files from the Nomad server, but you may download files from any other model as long as you know the URLs and they use HTTP protocol, right? So we have a block with libraries, a block with the download configuration, a block with our download function, and finally a block where we download the data. And in our libraries block, we are importing requests library, this one. And this is the library, right, for downloading files. It's a simple HTTP library for Python, okay? And here we configure the file we want to download, right? The date, in this case, today, the region, the resolution, the model cycle run, and the init and an interval hours. We have a function called download GFS, and I'm passing to that function 2 parameters, the date and the hour, okay? And here, I'm calling that function, download GFS, date, and hour, okay? And in each function call, I built the Nomad URL that we have seen in the Nomad website, but using code, right? there's a question. I'm not sure. There's a question in the chat box. I'm not sure if I missed it, but is there a link where all these scripts are available for download? Yes. And if you go to our Moodle page, Wayne, you will see in the beginning here, GitHub repository. Just click at it, and we will open the GitHub repository for this training. And there is a folder here called NWP. And you have all the scripts used in this demonstration, okay? Okay, thanks, Wayne, for your question. So in each function call, I manually build the URL. Remember in the Nomad's website, I have that field called show URL. And studying that URL, I was able to create this link here, right, for each resolution, okay? And that's what we are doing in our Colab notebooks, step number 4. This one. Download GFS data from the Nomad server, okay? Here are my functions, here are where I call the function, and here is the output in the terminal showing each step, okay? Now let's go. And by the way, this is another RGB and a very nice RGB called the simple water vapor. Let's go to our script number 13. And this is very important, right? We have seen how we may plot contours and that it opens some possibilities. And in our next demonstrations, we will learn how to plot streamlines, vectors, and barbs, okay? However, one important thing is that we need to learn how to read fields by selecting the level, right? Until now, we have seen examples with the 2-meter temperature, and as its name says, it's a single level variable. But we can also read variables that are available in multiple levels, and that is independent of the model you're using, right? And here's how you do it. In this example, we are going to plot the streamlines, and to plot the streamlines, we need to read 2 fields, the U component of the wind and the V component of the wind. Also, we need to specify the level that we want to read, because as we have seen in the Nomad server, we have variables for many levels, like 250, 500, 700, 980 hectopascals, for example. And in this example, we will download or plot the data, the streamlines at 250 HPAs, right? And the structure of these scripts for streamlines, vectors, and barbs are the same structure. They have these 4 blocks, always, right? The libraries block, data reading and manipulation block, the plot configuration block, the image generation block, okay? Here is how we choose the level. And it's not hard. We will use the same command from the PyGrid library called the select command, right here. But we will add a couple of arguments. The first one, the type of level. And in most cases, we need to insert isobaric in HPA. And the second argument is the level itself. In this example, 250, right? And that's it. So apart from that, in this example, we are reading more than one variable, because if you want to plot the streamlines, we need the U and V components of the wind. And here, we are reading the U component of wind, right? And we are calling it, we are storing it in the ucomp variable. But you may give any name you want. I'm calling it ucomp, right? And here, we are reading, with the select command, the V component of wind. also for 250 HPA. And we are storing the data inside the vcomp variable. And apart from the string lines, in this example, we also want to plot the wind speed, right? As a layer below the string lines, okay? So we need to calculate the wind speed because you do not have wind speed as a field, at least on GFS, okay? And it's not hard, as you see here, calculate the wind speed. We have the square root of the u squared and the v component also squared, right? And that's what we do here. Wind speed is equal to the square root function from numpy. And between parentheses, we have u component squared plus the v component squared. So at this point, we have the u component, the v component, and the wind speed. And now we can plot them, right? And as you can see here, in the last day, we have that big list of variables from our model field, from our model file. And we see that we have a variable named u component of wind, and that's our variable 276. And here we have the level 250 HPA, right? And that is how, when I was learning to process NWP data, that is how I have discovered the exact number of each field. U component of wind, U component of wind. Maybe in ECMWF, you have other names. But if you look at the list of names, you will be able to process ECMWF files too, okay? And here is how we plot the wind speed and the string lines. Plot the wind speed. It's not hard, right? We will use the same commands we have used to plot the 2-meter temperature, right? For example, contour F, contour, and sea level, when we are passing the longitudes, latitudes, and the wind speed, okay? And we are using a custom CMap, as we have learned in script number 7 or 8, okay? And here's the secret to plot the string lines, right? That's something new for us. We will use the matplotlib's string plot command, and this is a single line command, right? We need to pass some arguments. And in this example, we are passing the longitudes, right? Latitudes, the u component, the v component, and what is called the densities, right? And higher the densities, higher the density of the string lines. Also pass the line width of our string lines, and the color of our string lines in this example gray. Okay. And with the transform parameter, I'm just saying that just like we did with the GLM data, I'm telling Cartopy the coordinate system of my information. And with Edcori, I'm just saying that these are Cartesian coordinates. Okay? That's all we need. And this should be our result here, right? The wind speed in shades plotted below the string lines with a custom color map created the same way we have seen with the 2-meter temperature color map. And also the string lines with the characteristics I want, right? Here are some quick modifications, changing the appearance of the string lines. And let's go to Colab and make some changes. Let me run script number 13 in my Google Colab notebook. And we should have the string lines for today, 0 UTC, for 250 HPAs, right? This is the result. Let us wait a little bit. Here we have, right? This is for today, 0 AM. Okay. Now let me make some changes. So I'm going to make change the color. Let me see. I'm going to change the CMap of my wind speed to, for example, Let me zoom in. Too much. You change the color map of my wind speed to rainbow. And let me reduce the densities from 4 to 2. And let me change the colors of my streamlines from gray to black. Okay. I could also demonstrate how to increase the densities, but I will not do it now because when you increase the densities, it takes too much time to process. And that's something you need to take into account. Okay. And let's see our result. Let's wait a little bit. It is generating the PNG. And this should be your result here. Look, I have completely changed the appearance of my plot the way I want. Total control of the data, right? Another thing I can do is, instead of plotting the wind speeds as a layer, I could use it to use as a reference for the colors of my streamlines, right? However, using a color map in accordance to the wind speed. And let's see how we can do that. I'm going to command the contour command here, contour F, the contour and the C label, right? And now you change the string plot command. Let me copy it. I have created a copy of that command. Let me comment the old command. And I can change the string plot command as this, right? I need to pass another parameter called color after the densities, for example. Color, the color of my streamlines will be my wind speed, WS variable, okay? And I will ask, instead of colors, I will pass a parameter called CMAP. And I will say, for example, jet, right? Let me send this example in the chat box so you may test it with me. Now let me run the script again. And let me repeat, I'm using the wind speed as a reference for the color of my streamlines. And I'm also using a color map called jet, okay? Let's see the result. And this should be our result. Here we have. Look that we are not plotting the wind speed as another layer anymore. We are using field contours or unfilled contours or labels. We are using the wind speed itself as a reference to the color of my streamlines, right? Total control of the data. And that is how we work with streamlines, okay? We will jump script number 14 because it is very complex. But in a summary, we use a lot of code to animate the streamlines, as we are seeing here, right? And after we read the U and V components, we create some variables that will serve as a reference for our functions. And we configure the animation and call the functions that will create the animation. And as a result, you have the animated streamlines. As you see here, for South America, in this case, and for Caribbean region, okay? We will not explain each command, but you have the script available for you as a reference, right? And we can change the level or the variable be animated in this script number 14. All right, our script number 15 That's important. We will see how we can plot the same information, but using vectors instead of streamlines, which could be useful in some situations. The structure of the script is the same as you're seeing here, right? Libraries are the same. The data reading is the same, right? Read the U and V components using the select command, right? The only difference is that for this example, we are reading level 925 hectopascals, okay? Here, U component, V component, 925, 925. We also calculate the wind speed because we will plot it as a layer. And the difference is now that I'm plotting the vectors using the matplotlib quiver command. We were using the streamlines command. Now we are using the quiver command. And I just need to pass 4 parameters: longitudes, latitudes, the U component, and the V component, and that's it. However, in the quiver command, I do not have a density parameter. That is why to change the densities, I'm reading the pixels every 4 in this case, just like as we did with the GOZAR, just like as we did with the RGBs, etc. Right? So to reduce my density, I'm increasing these numbers here. And they all need to have the same dimensions. That is why I'm reading every 4 for all the variables. Okay? But how do I know which vector size is equal to a particular wind speed? So to make this identification, apart from the vectors, I'm adding at the upper part of my plot a single vector which has the size correspondent to a particular wind speed. And to do that, I'm using the quiver key command, right? And I need to say where I would like to add this label, right? In this case, I'm saying, hey, I would like to add this label in a position of 50% of the plot in the X direction, and 90%, approximately 90% of the plot height, 50% of the width, and 90% of the height, right? And I also would like to add a label correspondent, a vector correspondent to 20 knots. I would like to add a label written 20 knots, the right side of the vector, or in the east side. That's why I have an E here, right? So that is why I add a label to know the speed of the intensity of the vector, right? Magnitude of these vectors. And this should be the result, okay? The wind speed below is a field contour plot, the wind vectors overlaid with the wind speed contours. And above the image, we have our, which we call the quiver key of 20 knots in this example. But that's not strictly necessary, but I would like to show you that it is possible, right? And with some quick modifications, we can change the appearance of the vectors, we can change the densities, the colors, color map, etc. Now let's open Google Colab and make some tests with our script number 15. Here I have the animation, right? And here I have script number 15. What I will do is I will increase the densities from 4 to 2. Oh, and by the way, this is my original plot, okay? I will increase the densities. Instead of reading the pixels every 4, I will read them every 2 pixels. So I should have a greater density, right? So I will have twice as many vectors in comparison to my previous example, right? I'm running this script, right? Let's check the results. And here we have, I have many more vectors now, okay? And another thing I can do, just as I did with the streamlines, is removing the wind speed contours and coloring the vectors of my plot. So let me comment the contour command and the C-label command, and I will add another parameter to my command, right? I will add two parameters. First, the wind speed here, and CMap parameter here. Let me send this example command in the chat box. Let's see the result. You should have it after some seconds. And plotting vectors, like I'm going to show you, is very useful. For example, in some situations, right? And here I have some examples where I'm plotting the ASCAT winds from the METOP satellites. I'm using the same technique, so you can use it with satellite data also. Okay, and here we have the result. Okay, and look that my quiver key is not on the right position, and I could change it in the quiver key command. It's 71, so I just need to increase it so it is more in the upper part of my plot, right? Okay, and the last type of plot I would like to show you is the barbs. And in this example, we are not going to read only two variables from our model, but three, right? The U component of the wind, the V component of the wind, and the pressure reduced to mean sea level, right? Which is called pressure reduced to MSL. And how do I know that? Because I have that file with all my variables, okay? And for this pressure variable, we don't need to specify the level, because as it happened with the 2-meter temperature, and as the name of the variable says, this is a single level variable. However, for the U component and V component of the wind, I'm selecting, in this case, 850 HPAs, okay? And I'm calling this variable for the pressure pure air MLS, right? But you may call it any name you want. And apart from calculating the wind speed, I am dividing the variable by 100 to convert the pressure to hectopascals, okay? And here's how I can plot the barbs. First, to plot the pressures, we will use the contour plots just as we did before, okay? Contour F, just contour and C-label, right? And again, I'm using a custom color map using the technique I presented you in script number 7. And to plot the barbs is a little bit more complicated than the previous examples, right? And I will open a parenthesis here because we have a trick. But that trick is not that important for you because you are in the northern hemisphere. But for the southern hemisphere, according to the wind barb symbology, you need to flip the barbs, right? Otherwise, they will be plotted in the wrong direction in the regions below the equator. And for some reason, that is not done automatically by matplotlib, right? And how can we flip the barbs? Here's how we do it, right? Creating a variable called flip flag. And this variable will have the same size or the same shape of all the other variables. That is why I'm using the U component of the wind as a reference here. And I'm filling this matrix with zeros, with the numpy zeros command, right? After that, I'm saying here that for the latitudes below 0, I will put inside this variable called flip flag, you insert 1, because I need to use this variable as a flag in the future, right? And then I use this variable as a parameter for my plot. Now I'm closing the parameters, closing the parentheses here, right, about these barbs, because we will not need to do that if you are plotting only your region. But I need to do that for my region, okay? And to plot barbs with Python, we need to use here the barbs command. And we need to pass some parameters: longitudes, latitudes, the U component of the wind, the V component of the wind, the length of the barbs, right? If we want to display the barbs, even if it is 0, and I don't want to show them if they are 0, right? And the other characteristics of that barb: spacing, height, line width, and the barb color, gray in this case, right? And I'm also passing my final parameters, the flip bar parameters, with my flip flag, which is necessary for the southern hemisphere, okay? And this should be our result. The pressure reduced to mean sea level as field contours, and the barbs for 850 HPAs in this case, right? And here we have an example with a couple of plots without inverting the barbs and inverting the barbs for the latitudes below 0, right? And this is our meteorologist here. I didn't notice this for the first training. We organized it here, and our meteorologist says, "Hey, you need to invert the barbs," and then we found a way to invert them, right? And here we have some quick modifications. And again, changing the appearance of the barbs, densities, the colors, etc. Now let's make some tests with Google Colab and see the results. This is script number 16 in your Colab notebooks, barbs, right? And this is the result in the Colab notebook, right? However, this is the original plot without making any changes. But let's change the color of the barb, for example, to blue. Let's increase the line width to 1.5 instead of 8. 1.5 instead of 0.8. And let's increase the length to 6, right? And let's plot it again and see the results for today, right? Let's wait a little bit. If you have any questions, just let me know. Plotting the image, the green arrow shows where it is right now and showing the image. And here it is, right? I have the barbs in blue, or the color I want is the line widths I want, right? And just as we did with the streamlines and vectors, we can apply a color map to the barb itself. Passing the wind speed variable, for example, as an argument and adding a CMAP argument as jet. So I will copy the barb's instruction and I will add the wind speed as a parameter after the V component, right? I will pass the CMAP parameter, CMAP equal to jet, and I will delete the colors, the barb colors parameter, because it is not necessary anymore. Also, I'm going to comment my field contour plot. No, I will keep it the way it is because it's the pressure, not the winds. And let me run it again. And this should be our final example for today, right? Let's see the result. Oops, name NP is not defined. Let me check. Oh, it's not NP, it's WS, sorry. WS for wind speed, because that's the way I have called the variable, not NP. Let's run it again and see if we do not have any errors. Let me close my tabs because I have many tabs here. And this should be the result. Here we have, right? In this example, we are seeing the pressure reduced to mean sea level and the 850 HPA winds as barbs. The color of the barbs is related to the wind speed. Just to exemplify that we may control any aspect of the plot. All right? Okay, so we have seen different options that are available to plot NWP data. And again, you can use the same concepts to process any model, GFS, WRF, ECMWF, and others. And you may select any number of variables you want. And you may plot these variables the way you want and overlay them with the data you want, like satellite data. And that's the benefit of working with a programming language like Python and having access to grid files like we have in GeoNetcast Americas, right? For sure, it's a little bit more complicated than other options like GRADs, WinGrids, or Makaidas. However, we have more control of the information. And to me, the biggest benefit here is that you may use the same concepts to plot other data sets like satellite imagery using the same tool. And this facilitates things a lot. And now you have a better idea of how some software processes this information. Let's see the station for one of our users from Central America. Here you have these NWP plots, right? For example, we have, let me open it here. In this case, here, we are seeing the pressure, winds, total cloud cover, precipitation, and thickness for the next 10 days, okay? Let me open another example. And in this example, we have the relative vorticity and geopotential height, 500 HPA, for the next, I don't know how many days, 16, 17, May 18, 19, 12, 20, 21, 22, 23, 24, 25. We are 15 days ahead, okay, in this example, right? In this example. Here, we have, in this example, the accumulated precipitation for the next days, right? May 15, 16, 17, etc. And this is for the 0Z forecast cycle run, okay? Just to show a couple of examples more, here we have the precipitable water in millimeters and the cape. Okay? And I would like to show you one last example called the Galvez-Davidson index. And this is a thermodynamic index developed in 2014 to improve the forecast of tropical convection. And it was developed by Jose Galvez and Mike Davidson. And to create this tool, as it is called, it's not simple. And we need to read 9 variables from the model and apply many calculations, right? And what I would like to demonstrate now, not now, right? I will demonstrate that this Friday. So you understand the possibilities of working with Python is how we are able to calculate Galvez-Davidson index with Python. And this is the example number 18 in our Google Colab notebook. Okay? Here you have script number 18, and we will see that next Friday. And you can take a look at the next slides here, and we will explain this so you understand the possibilities. Okay? All right, and just a moment. And this is it for today. Okay, today we have seen how we may create the split water vapor and split ozone channel differences. And we have seen the FAZZT professional client, the software used to receive and manage the GeoNetcast Americas data. We have seen this software in detail. In the second session, we have seen the GeoNetcast Americas maintenance aspects and a maintenance checklist. And on Friday, I will access the station from Grenada, and we will check the FAZZT client and the maintenance checklist. It will fill this table with the parameters from the station from Grenada. And today we have finished the day with the second part of the DNWP data processing hands-on. And this Friday, we will begin the day learning how to create the dust, ash, and SO2 RGBs. And it is very, very interesting, right? We have very nice case studies. Also, you will learn how you may become a data provider of the system, right? And now that we know the basics of Python, we will learn how to use a better interface to develop our scripts. We will learn how to create advanced plots and animations, as we have seen in the assignment. And just as we have done in the first day with Panoply, we will continue to explore the GeoNetcast Americas content. And now is 12:30, and that's it for today. Thank you very much. And if you have any questions, you may send me an email. I'm very happy that some of you are trying to do the exercises and that you are managing to run scripts locally and in the cloud. And you may send me any number of emails you want. And I will post this afternoon the links shared during the presentation today. So thank you very much and see you this Friday. Bye-bye.